What if the smallest events in the universe could trigger the largest? Picture a single particle, so tiny it defies ordinary laws, suddenly appearing on the other side of an impenetrable barrier, like a ghost walking through walls. This isn't science fiction. It's quantum tunneling, one of the strangest and most awe-inspiring phenomena in physics. And here's the mind-blowing part. What if this bizarre quantum trick isn't just a microscopic oddity? What if, under the right conditions, it could scale up, way up, to reshape the cosmos itself? Think about the universe for a moment. Galaxies spin, stars explode, and black holes devour everything in their path. It all feels grand, unstoppable, governed by laws we think we understand. But beneath that majestic surface, reality is built on quantum foam, a seething, chaotic sea where particles flicker in and out of existence, where the impossible becomes routine. In that hidden realm, quantum tunneling lets particles cheat, bypassing barriers they shouldn't be able to cross. Now, stretch that idea to its cosmic limits. Could these tiny quantum shortcuts add up to something universe-shaking? Could they trigger events so vast they rewrite the fate of everything? That's the tantalizing mystery we're diving into today. From the bizarre rules that let particles teleport through walls to the wild possibility that quantum weirdness might one day crack open the fabric of space-time, we're about to explore how the smallest things could hold the keys to the biggest questions. Strap in. This journey will take us from the subatomic shadows to the edges of the observable universe, and by the end, you might never look at reality the same way again. The quantum world is calling. Are you ready to step through? To understand how quantum tunneling could rewrite cosmic rules, we first need to grasp how it works on the smallest scales, where the familiar laws of physics start to break down. Imagine tossing a ball at a wall. Classically, it would bounce back every time, but in the quantum realm, particles don't play by those rules. Thanks to wave-particle duality, everything electrons, protons, even entire atoms exists as both a particle and a spread-out wave of probabilities. This means a particle isn't just a tiny dot with a fixed location. It's more like a cloud of possibilities shimmering across space. That probability cloud is the key to tunneling. When a particle encounters an energy barrier, like an electric field or the crushing pressure inside a star, its wave nature means there's always a sliver of chance it could appear on the other side, as if it phased through an unbreakable wall. Think of it like this: if you rolled a die enough times, even the rarest outcome would eventually happen. In quantum terms, that outcome is a particle materializing where it shouldn't be. This isn't just theoretical. Your smartphone relies on tunneling every time you use it. Inside semiconductors, electrons tunnel through microscopic barriers to create the currents powering your device. Even stars harness this phenomenon. The sun shines because protons in its core tunnel through their mutual repulsion, fusing into helium and releasing energy. Without tunneling, stars including ours wouldn't ignite. But here's where it gets wild. If particles can bypass barriers on atomic scales, could similar effects emerge on cosmic ones? Could spacetime itself have quantum properties that allow tunneling like phenomena on a universe-sized canvas? We're venturing into speculative territory now, but the underlying principle holds. When reality is built on probabilities, even the impossible might just be waiting for its statistical moment. Quantum tunneling isn't just a far-out concept confined to labs or distant stars. It's hiding in plain sight, woven into the tech you use every single day. Take flash memory, the unsung hero inside your phone, laptop, and USB drives. Every time you save a photo or download an app, electrons tunnel through a thin, insulating layer to store data as microscopic ones and zeros. Without tunneling, your devices would lose their memory the moment you turn them off. It's like having a library where the books rearrange themselves unless you lock them in place quantum style. Then there's the MRI machine, a medical marvel that relies on tunneling to peer inside the human body. The superconducting magnets at its core only work because paired electrons tunnel through barriers, creating resistance-free currents. These magnets generate fields 50,000 times stronger than Earth's, letting doctors spot tumors or torn ligaments with astonishing clarity, without tunneling those life-saving scans. Gone, and let's not forget the scanning tunneling microscope, a device so precise it can image individual atoms by measuring how electrons tunnel across a needle's tip. Scientists use it to design new materials atom by atom, pushing the boundaries of nanotechnology. It's like having eyes that see the invisible, a superpower rooted in quantum quirks. So while tunneling might sound like science fiction, it's already here humming quietly in your pocket, saving lives in hospitals and unlocking secrets at the atomic scale. But if it can reshape our world on the small stage, what's stopping it from playing a far grander cosmic role? But how does this quantum trick jump from powering your phone to shaping the cosmos? To see the bigger picture, we need to shift our gaze from silicon chips to the stars, because tunneling isn't just a quirk of tiny particles. It's a universal cheat code written into the fabric of reality itself. Take black holes, those cosmic vacuum cleaners where gravity is so strong not even light can escape. Or can it? Thanks to tunneling, even black holes aren't perfectly black. At their edges, pairs of particles flicker in and out of existence. Normally, they'd annihilate each other instantly, but if one falls into the hole while the other tunnels away, the escaping particle becomes Hawking radiation, a slow leak that causes black holes to evaporate over eons. It's tunneling on a cosmic scale, proving quantum effects don't just vanish when things get big. They become the architects of stellar demise. Now stretch that logic further. If particles can tunnel out of a black hole's grip, could entire regions of spacetime pull off a similar escape? Some theories suggest our universe might have begun as a quantum fluctuation, a tunneling event where a speck of false vacuum burst into the cosmos we know. And if it happened once, why not again? Picture a hidden corner of spacetime under unimaginable pressure, suddenly tunneling into a new state. The resulting release of energy wouldn't just rewrite local physics, it could cascade outward at light speed, redefining the laws of reality across billions of light years. This isn't just hypothetical. Observations of dark energy, the mysterious force accelerating the universe's expansion, hint that empty space itself might be unstable. If so, a single quantum event could trigger a phase transition, rewriting the vacuum of space like a frozen lake cracking under its own weight. One moment, the universe as we know it. The next, a rewired cosmos where atoms, light, even time itself behave differently. From electrons hopping barriers in your devices to stars igniting in the void, tunneling threads through every scale of existence. And if the smallest cracks in reality can widen into cosmic ruptures, our universe might be far more fragile and far more astonishing than we ever dreamed. At the heart of quantum physics lies a truth so bizarre it challenges everything we think we know about emptiness. Space is never truly empty, not even in the deepest voids between galaxies. What looks like stillness to our eyes is actually a frenzy of activity, a microscopic chaos called quantum foam. Picture a bubbling ocean where particles and antiparticles materialize from nothing, dance for an unimaginably brief moment, then vanish back into the void. These aren't just metaphors, they're real fluctuations in the fabric of spacetime itself, driven by quantum tunneling on the tiniest scales. The math behind this is just as wild as it sounds. Thanks to Heisenberg's uncertainty principle, energy can't be pinned down perfectly, even in a vacuum. There's always a fuzziness, a budget of borrowed energy that allows particle-antiparticle pairs to blink into existence before annihilating each other. Normally, this happens too quickly to matter, but under extreme conditions like near a black hole's event horizon, as we've seen, one particle can tunnel away while its partner vanishes into the abyss, creating observable radiation. This same principle might explain why the universe isn't just cold, dead space. enter the Casimir effect, a mind-bending demonstration of quantum foam in action. Imagine two metal plates placed microscopically close in a vacuum. Normally, you'd expect nothing to happen, just empty space between them. But quantum fluctuations outside the plates have more room to wiggle than those squeezed between them. The result, an invisible pressure pushes the plates together, as if the vacuum itself is flexing its muscles. It's not magic, it's the cumulative effect of countless virtual particles tunneling in and out of existence, their fleeting lives warping reality on scales we can measure. Then there's zero-point energy, the idea that even at absolute zero, when all classical motion stops, space still thrums with this quantum static. It's the lowest possible energy state, yet it's far from zero. Calculations suggest the energy density of the vacuum should be staggering, enough to curl space-time into a knot. Yet our universe remains oddly smooth, hinting at mysteries we're still unraveling. Could this energy reservoir hide even grander tunneling phenomena? Some theories suggest these quantum whispers might one day amplify, triggering phase transitions that rewrite physics across the cosmos. From the hum of empty space to the fate of galaxies, quantum tunneling proves that nothing is ever truly quiet, truly still. The universe is alive with possibility, its foundations trembling with potential, and every so often that tremor might just shake the stars. Now consider this unsettling possibility. What if the universe is sitting on a knife's edge, not in its most stable state, but in a precarious pause, like a ball balanced halfway down a hill? That's the essence of the false vacuum hypothesis, and it's one of the most spine-chilling ideas in modern cosmology. Picture the fabric of space-time as a vast energy landscape full of peaks and valleys. Our universe might not be sitting at the very bottom, the true vacuum, where energy is at its absolute lowest. Instead, we could be stuck in a false vacuum, a temporary valley that seems stable but is primed for a catastrophic shift. Here's where quantum tunneling comes in. Just as a particle can unpredictably jump through a barrier, the universe itself might tunnel out of its false vacuum state, nucleating a bubble of true vacuum somewhere in space. This bubble wouldn't just sit there, it would expand in all directions at the speed of light, rewriting the laws of physics as it goes. One moment you're sipping coffee, oblivious. The next, an invisible wall of new reality sweeps through Earth, and suddenly atoms can't hold together, light can't propagate, and existence as we know it simply stops. This isn't just theoretical doom-mongering, the math checks out. In the lab, we've seen similar phase transitions like supercooled water suddenly freezing when disturbed. The universe could be in a supercooled state right now, waiting for a quantum nudge, and that nudge might already be underway in some distant galaxy, with a bubble of true vacuum racing toward us at light speed. We wouldn't see it coming, there'd be no warning, no time to react. The laws of physics themselves would change before we could even process what was happening. Yet there's a strange beauty in this fragility. The fact that quantum randomness could rewrite the cosmos reminds us how deeply connected the tiny and the titanic really are. From the flicker of particles in a vacuum to the fate of galaxies, tunneling bridges the scales, proving that the universe is far more dynamic and far more mysterious than it appears. Picture a single point in space, no larger than an atom, where the quantum chaos of the vacuum flickers just wrong. In that infinitesimal speck, the unthinkable happens. A random fluctuation tunnels through an energy barrier that should be impossible to cross. It's like rolling a billion-sided die and landing on the one forbidden outcome. But this isn't just a microscopic anomaly. This misstep in the quantum rules births a bubble, a sphere of true vacuum where the laws of physics are rewritten from scratch. Inside this bubble, gravity might weaken to a whisper or spike to crushing intensity. Light could slow to a crawl or cease to exist entirely. The fundamental constants that glue reality together, the strength of atomic bonds, the mass of electrons, even the passage of time, are no longer fixed. They're reshaped by this new physics, arbitrary and alien, and the bubble grows, not slowly, not predictably, but at the speed of light, its boundary a wall of annihilation where everything it touches is unmade. Here's the cosmic horror lurking in the math. If this bubble formed 100 light-years away, we'd have zero warning. One moment, the night sky would gleam with familiar stars. The next, an invisible sphere of oblivion would engulf Earth, and before your brain could register the change, your atoms would stop behaving like atoms. Molecules would unravel, space itself would reconfigure, erasing the rules that let life exist. No sound, no flash, just silence as physics itself is overwritten. The scariest part, this isn't fantasy. We've seen phase transitions before, like water freezing into ice or magnets flipping polarity when heated. The universe could be poised for its own transition, a quantum sneeze waiting to happen. And because the trigger is random tunneling, there's no countdown, no doomsday clock. It could happen tomorrow, or in 1 trillion years, or never. But the dice are rolling every second in every corner of space, and the odds aren't zero. Yet amid the existential dread, there's a twisted awe in realizing how fragile reality might be. The same quantum quirks that let stars shine and phones function could also undo everything, not with a bang but with a whisper. A single tunneling event amplified to cosmic scales, proving once again that the universe plays by rules far stranger than we dare imagine. The cosmic scale of quantum tunneling doesn't stop at hypothetical doomsday scenarios. It might hold the key to our universe's very birth. Rewind time 13.8 billion years past galaxies and stars, past the first atoms, to a moment so dense and hot that all known physics breaks down. What sparked the Big Bang? The answer could lie in a process eerily similar to false vacuum decay, where our entire universe tunneled into existence from nothingness. Inflationary cosmology paints a startling picture, a speck of primordial space smaller than an atom, suddenly ballooning to cosmic size in less than a blink. But what powered that explosive expansion? Some theories suggest it began with a quantum fluctuation, a tunneling event where a patch of false vacuum dropped into a lower energy state, releasing unfathomable energy. Think of it like a supercharged version of water freezing into ice, except instead of releasing heat, it spat out an entire universe. The math reveals something hauntingly elegant. The equations governing false vacuum decay align suspiciously well with those describing cosmic inflation. Both involve metastable states, both unleash cascading energy, and both rewrite reality in their wake. This isn't just philosophical speculation. Observations of the cosmic microwave background, the afterglow of the Big Bang show patterns that match inflationary predictions with uncanny precision. Those faint temperature variations in the night sky, they could be quantum fluctuations from the universe's first trillionth of a second, stretched to galactic scales by inflation. It's as if we're reading quantum fingerprints left on the cosmos itself. Now zoom out further. If one universe can tunnel into being, why not many? Enter the multiverse, a frothing sea of bubble universes, each born from separate tunneling events, each with its own unique physics. Some might have stronger gravity, making stars burn out in moments. Others could lack electromagnetism, preventing atoms from forming. Our universe, with its Goldilocks perfect constants, might just be one accidental winner in an infinite cosmic lottery. The implications are dizzying. The same quantum trick that powers your phone could have birthed everything, every galaxy, every planet, every conscious thought. From subatomic quirks to the vastness of creation, tunneling stitches reality together across scales we're only beginning to fathom. And if true, it means the universe isn't just strange. It's stranger than we can possibly imagine. Dark energy, the mysterious force stretching our universe apart at an ever-increasing pace, might be the ultimate cosmic wildcard when it comes to quantum tunneling's universe-altering potential. On one hand, this relentless expansion could be diluting space-time to the point where tunneling risks fade into irrelevance. Picture a rubber sheet being pulled so thin that even quantum wrinkles can't form. The energy barriers separating false vacuum from true vacuum might stretch beyond reach, leaving the universe frozen in its current state indefinitely. Some theorists argue this is our best-case scenario, a cosmic safety net woven by acceleration itself, but flip the argument and dark energy takes on a far more ominous role. What if the same expansion that seems to stabilize the vacuum is actually priming it for catastrophe? As space stretches, regions of false vacuum could become isolated, like bubbles forming in boiling water. In these pockets, quantum fluctuations might tunnel unimpeded, triggering localized phase transitions that, given enough time, could merge into a universe-wide rewrite. It's a paradox. The very force keeping galaxies apart could be creating ideal conditions for vacuum decay in the voids between them. The math splits into two starkly different camps. One set of models suggests dark energy's weak but persistent push raises the energy needed for tunneling, making spontaneous vacuum collapse astronomically unlikely. Other simulations show the opposite, that in an eternally expanding universe, the probability of a tunneling event doesn't just persist, it approaches certainty over infinite time. The debate hinges on whether the quantum foam gets stretched out or concentrated by cosmic expansion, and even top physicists can't agree on which effect dominates. Observational data only deepens the mystery. Measurements of distant supernova confirm dark energy's acceleration, but they can't tell us whether it's a constant force or something evolving over time. If dark energy strengthens, it might one day rip apart atoms in a Big Rip scenario long before tunneling becomes a concern. If it weakens, the universe could revert to a state where quantum instabilities reign. We're left watching the cosmos play a high-stakes game of tug-of-war, with tunneling on one end of the rope and expansion on the other, and no one knows which side is stronger. This isn't just academic chess. The outcome determines whether our universe dies cold and quiet or hot and sudden. Either way, the dance between quantum chance and cosmic forces reveals a profound truth. Reality's stability was never guaranteed. It's a temporary arrangement, a ceasefire in the laws of physics that could, at any moment, be revoked by the universe's deepest, smallest whispers. The numbers surrounding vacuum decay straddle the line between unnerving and absurd. On one end of the spectrum, calculations suggest a universe-ending tunneling event could strike tomorrow, a cosmic lightning bolt with zero warning. On the other, the odds might be so vanishingly small that you'd need to wait 10 to the 100th power years, a 1 followed by 100 zeros before witnessing it. That's a time span so vast it makes the age of our universe look like a single blink in eternity. So why aren't physicists boarding metaphorical arcs? First, consider how probability operates at these scales. Yes, quantum tunneling is random, but there's a reason we don't panic about every subatomic roll of the dice. The energy barrier keeping our false vacuum stable, while not insurmountable, is staggeringly high. Picture trying to throw a baseball over Mount Everest from sea level. Possible, technically, if you could throw it at near light speed. Likely, not even remotely. The universe's current configuration sits in an exceptionally deep valley, and tunneling out requires a freak fluctuation of cosmic proportions. Then there's observational evidence, or rather, the lack of it. If vacuum decay were a frequent cosmic occurrence, we'd expect to see telltale bubbles of new physics expanding through space. Yet the sky shows no signs of such anomalies. Distant galaxies billions of light-years away, snapshots of the universe's past, still obey the same laws we do. No mysterious regions where gravity reverses or matter dissolves. If decay bubbles exist, they're either extraordinarily rare or expanding toward us at light speed, invisible until arrival. But here's the twist. Even if the probability is minuscule, the consequences are so absolute that some researchers treat it as a philosophical puzzle rather than a practical threat. Existential risks often get categorized by their likelihood and impact. Asteroid strikes, rare but manageable with early detection. Artificial intelligence misalignment. Uncertain but worth proactive safeguards. Vacuum decay, potentially inevitable over infinite time, yet impossible to prevent or escape if initiated. This puts it in a bizarre category where worry is both justified and utterly pointless, like fearing the heat death of the universe while making breakfast. That said, science thrives on testing the untestable. Recent work with ultra-cold quantum fluids has allowed physicists to simulate false vacuum decay in the lab, observing how microscopic bubbles of new phases nucleate and spread. These experiments don't replicate cosmic scales, but they validate the underlying math, proving such transitions aren't just theoretical. Meanwhile, astronomers scrutinize ancient light for anomalies, hunting for any hint that distant regions of space might operate under different physical constants. So while the numbers might swing from imminent to effectively never, the real takeaway is how quantum uncertainty permeates existence itself. From the certainty of sunrise tomorrow to the eventual fate of galaxies, everything carries an asterisk, a whisper of probability that keeps the cosmos endlessly unpredictable. And perhaps that's the most profound lesson of all. Reality isn't just stranger than we imagine, but stranger than we can afford to ignore. Here's where things get truly mind-bending. What if the universe itself is paying attention? Quantum mechanics has long grappled with the observer effect, the strange idea that measurements don't just record reality but shape it. In classic experiments like the double slit, particles behave as waves until someone observes them, at which point they collapse into definite positions. But what counts as an observer, a human, a machine, or could consciousness itself be the key? Some interpretations, like von Neumann and Wigner's, take this even further, suggesting that conscious observation is the only thing that forces quantum possibilities to crystallize into concrete reality. Now stretch that idea to the cosmic scale. Most of the universe is empty voids between galaxies stretching millions of light years with no stars, no planets, no conscious beings to look. If observation stabilizes quantum states, could these barren regions become playgrounds for unchecked quantum weirdness? Without observers to collapse probabilities, maybe particles tunnel more freely, barriers weaken, and the vacuum itself grows restless. It's a haunting thought. The emptier space gets, the more unstable it might become, like a house crumbling faster in the absence of anyone to notice the cracks. Critics argue this leans too heavily into philosophy, equating consciousness with some mystical force. After all, detectors and cameras can collapse wave functions without human involvement. But the deeper question lingers. What if the act of measurement, conscious or not, alters the likelihood of quantum events? In empty space where no detectors flicker, tunneling might not just be probable. It could be inevitable. Imagine a galaxy far beyond our observational horizon where quantum fluctuations go unchecked. There, a single unobserved particle's tunneling might cascade, nucleating a bubble of new physics that expands unseen. By the time it reaches us, the universe behind it could already be rewritten. It's a paradox wrapped in a riddle. The places we least observe might be where reality is most fluid, where the quantum dice roll without anyone to tally the results. Whether consciousness shapes reality or not, one thing is clear: the universe isn't just a backdrop, it's an active participant, its behavior shifting based on whether anyone or anything is watching. And in the deepest voids, where no eyes gaze and no instruments hum, the quantum rules might just play out differently, turning empty space into a laboratory for the impossible. Black holes aren't just cosmic vacuum cleaners, they might be quantum tunneling powerhouses, warping the rules of reality in ways that could rewrite the universe's fate. At the edge of a black hole's event horizon, gravity stretches space-time into a singularity, a place where all known physics breaks down. In that chaos, quantum effects don't just persist, they amplify. Imagine the vacuum fluctuations we've talked about, those particle-antiparticle pairs blinking in and out of existence but now cranked to extremes. Near a black hole, tidal forces stretch spacetime so thin that tunneling isn't just probable, it's inevitable. Particles that would normally annihilate each other in a heartbeat get torn apart, with one falling into the abyss while the other tunnels away as Hawking radiation. But what if this process isn't just a slow leak? What if, under the right conditions, it becomes a cosmic geyser? Enter Roger Penrose's conformal cyclic cosmology, a mind-bending theory where black holes might serve as bridges between universes. In this model, our universe's distant future, a cold, dark expanse devoid of stars, could undergo a mathematical transformation, rescaling infinite spacetime into a new Big Bang. The trigger, black holes evaporating via quantum tunneling, their energy not vanishing but recycling. Picture a dying universe where the last remaining structures are supermassive black holes, slowly radiating away via Hawking radiation until bam, their final tunneling events spark a new cosmic cycle. It's as if black holes are cosmic seeds, their deaths birthing fresh universes where the constants of physics might shuffle like a deck of cards. Now take it further. Some theories suggest that when a black hole's tunneling reaches critical mass, it doesn't just fade, it explodes, not with matter and light, but with something far stranger, a white hole, the theoretical opposite of a black hole where spacetime erupts outward. If black holes are drains, white holes are fire hoses spewing out everything they've ever consumed. And here's the wild part. White holes might not just be mathematical curiosities. Observations of bizarre gamma-ray bursts, ultra-high-energy explosions with no clear source hint that these cosmic detonations could be tunneling events on a galactic scale. A black hole's interior, stretched to its quantum limits, might tunnel into a white hole's outburst, rewriting its own demise as a rebirth. This isn't just poetic speculation. The math of loop quantum gravity, a leading theory uniting quantum mechanics and relativity, allows for such transitions. In this framework, a black hole's collapse doesn't end in a singularity but rebounds like a compressed spring, tunneling into a white hole explosion. The energy release would be catastrophic, visible across billions of light years. And if even one of these events has happened in our cosmic backyard, we might already have detected its echo in the static of deep space telescopes. From Hawking radiation to white hole fireworks, black holes are proving to be far more than gravitational traps. They're laboratories for the most extreme quantum tunneling events imaginable, where spacetime's fabric is so stressed that reality itself starts to fray. And if Penrose and others are right, these monstrous voids might not just be the end of things, they could be the beginning of everything else. Dark matter might be the universe's quietest conspirator, an invisible architect shaping galaxies while leaving barely a trace of its existence. But what if its influence runs deeper than gravity alone? What if these mysterious particles don't just hover in the cosmic shadows, but actively participate in quantum tunneling events capable of rewriting reality? Enter actions, one of the leading candidates for dark matter. These hypothetical particles, originally proposed to solve a puzzle in particle physics, could be far more than passive placeholders in the cosmic ledger. Their quantum properties might make them uniquely suited to trigger phase transitions on scales we've barely begun to imagine. Picture an action drifting through the void. Unlike ordinary matter, it doesn't interact with light or electromagnetism, but it does have a strange relationship with quantum fields. In certain high-energy environments like the hearts of neutron stars or the swirling disks around black holes, actions could tunnel through barriers that would stop normal particles cold. If enough of them gather in one place, their collective tunneling might nudge a quantum field out of its false vacuum state, sparking a chain reaction. It's like a crowd of invisible hands pushing on a cosmic lever, hidden from view but capable of seismic consequences. This isn't pure speculation. Experiments at CERN are already hunting for signs of exotic particle decays that could hint at these processes. The Na-62 and CAS detectors, for instance, are tuned to catch glimpses of actions or action-like particles, watching for the telltale flickers of energy that might betray their presence. And while no smoking gun has been found yet, the mere possibility sends ripples through theoretical physics. If actions or another dark matter particle can tunnel en masse, they might not just explain missing galactic mass. They could be the silent puppeteers behind vacuum decay, cosmic inflation, or even the birth of new universes. The implications are staggering. Dark matter's true role might not be limited to holding galaxies together. It could be an active participant in the universe's quantum theater, capable of rewriting the script when least expected. And if experiments like those at CERN ever catch these particles in the act, we might discover that the cosmos's greatest mystery is also its most potent architect of change. What if quantum tunneling isn't just a quirk of physics, but a literal glitch in the fabric of reality? This isn't idle speculation. If the simulation hypothesis holds water and our universe runs on some unfathomable cosmic computer, then particles tunneling through impossible barriers might be less like natural phenomena and more like errors in the code. Think of a video game where a character clips through a wall because the physics engine hiccuped. Now scale that up to reality itself, where the engine is the underlying rules of existence, and tunneling becomes a bug the programmers never patched. Nick Bostrom's famous simulation argument lays the groundwork here. If advanced civilizations could one day run ancestor simulations, hyper-detailed recreations of their past, then the statistical likelihood we're living in base reality shrinks to near zero. In that framework, quantum tunneling takes on an eerie new meaning. Glitches in simulated worlds wouldn't be random, they'd emerge from limitations in processing power or memory allocation. Maybe the simulation can't perfectly calculate every particle's position, so occasionally it fudges the math, letting things tunnel where they shouldn't. The Heisenberg uncertainty principle, just a clever way to reduce computational load by not tracking everything at once. Here's where it gets trippy. If tunneling is a glitch, it might not follow consistent rules. In our universe, tunneling probabilities are predictable. Electrons have certain odds of hopping barriers. Stars fuse hydrogen at measurable rates. But in a simulation with finite resources, those probabilities could drift over time as the system optimizes itself or degrades. Ancient light from distant galaxies might hold clues. If tunneling rates subtly change across cosmic epochs, it could suggest the programmers are tweaking parameters behind the scenes. Even stranger, vacuum decay could be less a natural process and more a cascading failure, a cosmic blue screen of death. Imagine a corruption in the code governing the Higgs field, spreading at light speed until the simulation crashes. The scariest part, we'd never see it coming. One moment, reality runs smoothly. The next, the system reboots and we cease to exist, not because of physics, but because someone, somewhere, hit Control-Alt-Delete. But before you panic, consider the flip side. If we're in a simulation, tunneling glitches might also be our salvation. Hackers exploit bugs to jailbreak systems. Could we one day exploit quantum tunneling to manipulate the simulation itself? Scientists already use tunneling to probe atomic structures with insane precision. In a simulated universe, that same tech might let us peek at the source code or even rewrite it. Bostrom's hypothesis forces a chilling question. If reality is software, who's to say the programmers didn't build fail-safes? Maybe vacuum decay isn't a bug but a feature, an emergency reset button for universes that grow too chaotic. Or perhaps tunneling is a diagnostic tool, letting the simulators test the boundaries of their creation. Either way, the idea transforms quantum mechanics from a set of abstract rules into something far more intimate, the hidden UI of existence, where every particle's dice roll might just be a line of code waiting to be debugged. The cosmic microwave background, that faint glow left over from the Big Bang, might be hiding forensic evidence of universe-altering tunneling events in our distant past. Picture this ancient light as a cosmic fingerprint, its subtle imperfections encoding secrets about reality's turbulent infancy. Among its most puzzling features are so-called cold spots, regions of space where the temperature dips just slightly lower than the surrounding haze. One in particular, spanning nearly 2 billion light-years, defies conventional explanations. Some theorists propose it's more than a statistical fluke. It could be the scar of a primordial tunneling event, a bubble of false vacuum decay that nearly rewrote physics before fizzling out. The math is provocative. If a quantum fluctuation in the early universe triggered a partial phase transition, a tunneling event that started but didn't complete, it would leave behind a disturbance in spacetime's fabric. As this disturbance expanded with the universe, it would subtly alter how light traveled through space, cooling photons in its wake like a shadow frozen in time. Simulations show such an event could produce cold spots with precisely the observed size and temperature anomaly. It's as if we're staring at a fossilized quantum hiccup, a moment when reality almost took a different path. Then there's the lithium problem, a nagging mismatch between theory and observation. According to Big Bang nucleosynthesis models, the universe should have produced 3 times more lithium-7 than we actually detect in ancient stars. Traditional fixes like tweaking nuclear reaction rates haven't closed the gap, but introduce a tunneling twist and the puzzle starts to make sense. If regions of the early universe experienced temporary changes in fundamental constants due to quantum tunneling, say, a fleeting shift in the strong nuclear force, it could disrupt lithium production just enough to match observations. These aren't minor adjustments, they're cosmic rewrites etched into the periodic table itself. The hunt for proof is accelerating. Next-generation telescopes like the Simons Observatory are mapping the microwave background with unprecedented precision, searching for telltale patterns around cold spots that might betray tunneling's handiwork. Meanwhile, astrophysicists are re-examining the spectra of primordial stars, looking for isotopic anomalies that could signal ancient physics violations. Even particle colliders are in on the act. Experiments at CERN are recreating extreme conditions akin to the universe's first microseconds, watching for signs of vacuum instability that might parallel these cosmological clues. What's staggering isn't just the possibility that quantum tunneling left marks on the infant universe, it's that those marks might still be visible today, waiting in the data like cosmic breadcrumbs. If confirmed, they'd offer something extraordinary, empirical evidence that reality's foundational rules aren't just flexible on quantum scales, but were bent catastrophically when the cosmos was young. The implications would ripple through physics, forcing us to confront whether our universe is a one-time accident or just one thread in a tapestry of realities, each born from a quantum roll of the dice. What if quantum tunneling isn't an end but a beginning, a cosmic stitch weaving separate realities together? Picture this: 2 universes, each with their own laws of physics, drifting through higher dimensional space like sheets in the wind. At some point, their quantum fringes brush against each other, and in that fleeting contact, particles tunnel across the divide. Suddenly, what was separate becomes entangled. This isn't just theoretical poetry. It's a serious possibility within brain cosmology, where our universe might exist as a 3-dimensional brain floating in a higher dimensional bulk. In that hidden geometry, tunneling could act as a bridge, letting entire regions of spacetime merge or collide. Max Tegmark's Multiverse framework takes this even further. His Level 1 multiverse suggests infinite copies of our cosmos, born from quantum fluctuations during inflation, all governed by the same physics but with slight variations, like a cosmic hall of mirrors. But Level 2 is where tunneling gets wild. Here, separate bubble universes, each with unique physical constants, nucleate from false vacuum decay. Normally, these bubbles expand eternally, never touching. Yet if quantum tunneling warps the barriers between them, adjacent universes might temporarily overlap, trading particles or even swapping laws of physics. Imagine a region of space where gravity weakens overnight because a neighboring universe's quantum rules bled through. The evidence for such mergers is speculative but tantalizing. Some physicists point to anomalies in the cosmic microwave background, unexplained cold spots or strange polarization patterns as potential scars from ancient brain collisions. Others suggest that dark flow, the mysterious motion of galaxy clusters in a single preferred direction, could be the gravitational tug of a parallel universe brushing against ours. Even more radical is the idea that cosmic inflation never truly stopped, that our universe is still subtly expanding into others, with tunneling events acting as cosmic synapses firing between cosmic brains. The implications are dizzying. If universes can merge, then nothing is truly isolated. A tunneling event in a distant reality might one day rewrite our own physics, not with destruction but with quiet convergence. It's a humbling thought. The same quantum quirk that lets electrons cheat their way through barriers might also weave the multiverse into a single, ever-changing tapestry. And if that's true, then reality isn't just stranger than we imagine, it's stranger than we can afford to imagine alone. What if consciousness itself has been harnessing quantum tunneling all along, not as some abstract physics phenomenon, but as the very substrate of thought? This isn't just wild speculation. It's the spine of a radical theory called ORCH, or championed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their idea flips conventional neuroscience on its head. Consciousness isn't merely the product of neurons firing like biological circuits. Instead, it emerges from quantum computations happening inside microtubules, tiny protein structures within brain cells. And here's the kicker: these computations rely on tunneling. Think of microtubules as quantum orchestras. Electrons within them don't just hop between energy states classically. They tunnel through barriers, collapsing probabilities into conscious moments. This isn't just poetic metaphor. Anesthesia, which switches off awareness without killing brain cells, might work by disrupting these delicate quantum dances. If tunneling underlies perception, then consciousness isn't a passive observer. It's an active participant in shaping reality at the quantum level. Now stretch that idea to cosmic scales. If tunneling flickers at the heart of human awareness, could the universe itself harbor a form of proto-consciousness, panpsychism? The view that mind is fundamental to matter suggests yes. In this framework, even particles might possess rudimentary experience, and tunneling could be how the cosmos thinks. Picture vacuum fluctuations as cosmic synapses firing, with each tunneling event a fleeting thought in the mind of the universe. But here's the twist: if consciousness and tunneling are entwined, could a universal mind suppress tunneling to stabilize reality? Some models propose that observation, whether by humans or some deeper cosmic awareness, collapses quantum probabilities, reducing chaos. In empty space where no observers exist, tunneling might run rampant, birthing new physics. But in regions rich with consciousness, like Earth, the act of observation could act as a cosmic damper, keeping tunneling in check. It's a dizzying loop. We're products of quantum randomness, yet our very awareness might tether that randomness into order. Critics dismiss ORCH and panpsychism as untestable metaphysics. But consider this: recent experiments with quantum biology show photosynthesis in plants hinges on tunneling for near-perfect energy efficiency. If nature exploits tunneling for survival, why not for cognition? And if the universe's fabric is inherently mental, then tunneling isn't just a glitch in physics. It's the universe whispering to itself, one probabilistic thought at a time. Time crystals sound like something ripped from a science fiction epic, structures that pulse with rhythm, not in space, but in time itself, defying entropy's relentless march toward chaos. First proposed by Nobel laureate Frank Wilczek, these exotic phases of matter don't just exist, they persist, cycling through states indefinitely without energy input, like a clock that ticks forever without winding. At their core, time crystals exploit quantum entanglement and many body interactions to lock themselves into a stable, repeating pattern, a kind of temporal symmetry breaking that physics once deemed impossible. Now imagine harnessing that same stubborn stability to confront the universe's ultimate existential threat, vacuum decay. If a bubble of true vacuum began devouring spacetime, could time crystals act as cosmic speed bumps, slowing or even halting its advance? Wilczek's vision hinges on a radical idea that time crystals might achieve what no ordinary matter can: dynamic equilibrium in the face of phase transitions. Picture a sheet of ice spreading across a lake. Normally, it freezes unchecked, but drop in a time crystal, and its relentless oscillations could, in theory, disrupt the ice's growth, creating zones where freezing stalls. Translate that to the quantum vacuum, and these structures might locally reinforce false vacuum states, their rhythmic coherence acting as a shield against decay. Experiments with trapped ions and superconducting qubits have already created primitive time crystals in labs, proving their behaviors aren't just mathematical curiosities. Scale that up, and who's to say they couldn't influence the fabric of spacetime itself? Critics argue that time crystals, for all their intrigue, are too fragile to withstand cosmic scale upheaval. Their stability relies on isolation from external noise, something the quantum foam of a decaying vacuum would drown out in an instant. But here's the twist: some models suggest time crystals could arise naturally in extreme environments like neutron star crusts or black hole accretion disks, where gravity and quantum forces collide. If so, the universe might already be littered with these temporal oddities, quietly anchoring pockets of order against chaos. The implications spiral outward. If we could engineer macroscale time crystals, a feat still firmly in the realm of theory, they might offer more than just physics puzzles. They could be tools, letting us probe the boundaries of entropy, causality, and even the arrow of time. And if vacuum decay is the universe's ultimate expiration date, time crystals might just be the loophole that buys eternity, not by fighting the laws of physics, but by dancing to their deepest, most hidden rhythms. The Fermi paradox has haunted scientists for decades. Where is everybody? If the universe is so vast and ancient, why does it echo with silence? One terrifying answer might be hiding in the quantum shadows. Vacuum decay could be the ultimate great filter, a cosmic trapdoor swallowing civilizations before they ever get the chance to shout into the void. Imagine a species reaching technological maturity, experimenting with high-energy physics to unlock the secrets of reality, only to accidentally nudge a quantum field past its tipping point. A single miscalculation, one experiment too many, and a bubble of true vacuum begins expanding at light speed, erasing not just their planet, but their entire galactic neighborhood from existence. The grim elegance of this scenario: it leaves no ruins, no warning beacons, just pristine, empty space where intelligence once flickered. But not everyone buys the doomsday argument. Optimists point out that if vacuum decay were a common fate, we'd likely see signs of it: anomalous energy signatures or sudden vanishings of distant galaxies. The cosmic microwave background, our universe's baby picture, shows no obvious scars from such catastrophes. Maybe civilizations smart enough to toy with universe-ending physics are also smart enough to recognize the danger, building fail-safes or even spreading beyond their home systems as a hedge against annihilation. Others speculate that advanced beings might leave deliberate warnings, like coded messages in pulsar patterns or engineered relics shouting, "Don't touch this," in the language of particle physics. The debate splits along a philosophical fault line. Pessimists argue that the absence of such warnings is itself evidence civilizations that discover vacuum decay don't survive to teach others. Optimists counter that we might just be early to the party, with most intelligence arising in eras when the universe is colder and safer. Or perhaps the filter isn't behind us at all, but ahead, a hurdle we haven't faced yet. The unsettling truth is that both scenarios hinge on unknowns. We're like ants debating whether humans exist based on the absence of footprints in our anthill. Yet buried in this cosmic puzzle is a strange hope. If vacuum decay hasn't already erased all advanced life, maybe the great filter isn't inevitable. Maybe we're living in a universe where physics permits civilizations to navigate the minefield, where tunneling isn't a death sentence but a challenge to be solved. The silence of the stars could mean we're alone, doomed, or simply listening wrong. Until we know one thing's certain, every quantum experiment isn't just science. It's a gamble with reality itself. The idea that a lab experiment could accidentally rewrite the universe sounds like a bad sci-fi plot until you run the numbers. Particle colliders like the Large Hadron Collider at CERN routinely smash protons together at energies mimicking the universe's first trillionth of a second. Could these man-made fireballs, however brief, nudge a quantum field past its tipping point? The nightmare scenario goes like this. A high-energy collision creates an exotic particle, say a strangelet, that catalyzes vacuum decay, converting normal matter into something unrecognizable. Suddenly, the experiment that unlocked the Higgs boson becomes the button that ends reality. Before you panic, know this: physicists take these risks dead seriously. The LHC's safety assessments read like doomsday contingency plans. Strangelets, for instance, were scrutinized long before the first proton beams circulated. The verdict, even if they form, are big if they'd be unstable, decaying faster than they could wreak havoc. The math is reassuring. Cosmic rays have bombarded Earth with far higher energies for billions of years without triggering vacuum decay. If nature hasn't done it, why would our puny colliders? Yet the debate isn't purely scientific, it's ethical. Labs now weigh existential risk alongside discovery, a shift crystallized by CERN 2008 safety review. Critics argue we're playing with forces we don't fully control. Proponents counter that without pushing boundaries, we'd still think the atom was indivisible. The tension mirrors nuclear physics in the 1940s. The same equations that lit stars also built bombs. Quantum computers add another layer. Unlike colliders, they don't brute force energy barriers, they exploit quantum effects directly. Hypothetically, a powerful enough quantum system could simulate vacuum states so precisely it accidentally replicates one. Think of it as a digital Ouija board. The more accurately you model a ghost, the likelier it manifests. Current devices are nowhere near this threat level, but theorists already game out safeguards like confining simulations to isolated quantum environments. Ultimately, the scariest part isn't the physics, it's the hubris. We're cosmic toddlers fiddling with forces that dwarf us. Yet every great leap from fire to fusion began with someone ignoring the warnings. The line between recklessness and progress blurs when the stakes include not just our survival, but reality itself. Maybe the real safeguard isn't better math, but the humility to ask, just because we can, does that mean we should? Detecting an existential threat like vacuum decay requires more than just theory. It demands real-world tools capable of sensing the universe's subtlest whispers. One proposed early warning signal: shifts in fundamental particle masses. The Higgs field, which gives particles their mass, would be the first domino to fall in a vacuum decay scenario. If its energy state began fluctuating, electrons or quarks might suddenly weigh fractionally more or less, a change imperceptible to scales but glaring to precision instruments. Experiments like CERN Precision, Higgs measurements, or Fermilab's mu1G-2 could spot anomalies long before catastrophic effects manifest. Imagine a smoke detector for spacetime itself, chirping at the first whiff of quantum instability. Then there's the neutrino paradox. These ghostly particles barely interact with matter, yet a sudden burst of high-energy neutrinos with no apparent source might signal a tunneling event in progress. When a false vacuum bubble nucleates, it could release a shockwave of particles as it rewrites physics at its boundary. projects like Ice Cube in Antarctica or Japan's Super Kamiok and monitor neutrino fluxes around the clock. An unexplained spike, especially if paired with strange energy signatures, might be our only heads-up before the cosmic rewrite reaches our doorstep. But the most haunting clues could come from the ancient light of distant galaxies. If vacuum decay triggered somewhere in the observable universe, its expanding boundary would distort photons passing through it. The James Webb Space Telescope's deep field images might reveal patches where light curves unnaturally or spectral lines shift abruptly, like seeing a ripple in a pond where no stone was thrown. MIT's quantum sensor projects take this even further, developing devices so sensitive they could detect spacetime's quantum fuzziness thickening in real time. These sensors exploit entangled atoms to measure gravitational waves and other phenomena with nanometer precision. If spacetime itself began fraying at the edges, they'd likely be the first to know. The challenge isn't just spotting these signals, it's interpreting them before it's too late. A neutrino burst could mean a supernova. Shifting particle masses might be experimental error. But collectively, these anomalies would form a pattern no natural phenomenon could explain. The real race isn't against the decay itself, it's against our ability to recognize the universe's final cry for help hidden in the noise. And that's a race where second place doesn't exist. Faced with a universe that could rewrite itself at any moment, humanity's survival might hinge on ideas so bold they blur the line between science and speculation. One radical proposal, building cosmic shield structures designed to reinforce spacetime itself against vacuum decay. Picture massive orbital rings of superconducting material, charged to energies that stabilize the Higgs field in their vicinity. These wouldn't be physical barriers in the traditional sense, but quantum anchors, their electromagnetic fields tuned to subtly nudge vacuum fluctuations back toward safety. The math suggests such devices could, in theory, create localized pockets of pinned false vacuum, buying time even if decay began elsewhere. Of course, engineering on this scale dwarfs anything we've attempted. Think Dyson spheres with a side of particle physics, but the principle echoes technologies we already use. MRI machines manipulate quantum states in tiny volumes. Scaled up, could they do the same for spacetime? Then there's the ultimate Hail Mary, fleeing the universe altogether. If decay's frontier moves at light speed, faster than light travel becomes the only escape. Alcubierre warp drives, hypothetical engines that contract spacetime ahead of a ship while expanding it behind, offer one pathway. By riding a bubble of distorted spacetime, a vessel could outpace decay's expansion without violating relativity. The catch: warp drives require exotic matter with negative energy, something that may not exist. Yet experiments with Casimir cavities and quantum optics have produced microscopic regions of negative energy, proving the concept isn't pure fantasy. A more pragmatic alternative might be relativistic arc ships, traveling at near light speeds to buy millennia in subjective time while hunting for cosmic regions where decay hasn't reached. Either way, the strategy is the same: run faster than reality can collapse. For those who'd rather cheat than retreat, creating a baby universe offers a bizarre loophole. The idea hinges on manipulating a quantum fluctuation to nucleate a new spacetime bubble, then somehow tethering it to ours. Physicists like Alan Guth have theorized that sufficient energy concentration, say, from a black hole collision or a particle accelerator the size of a solar system, might birth a new cosmos with its own laws. If the umbilical cord between universes could be stabilized, data or even consciousness might be shuttled across before the old universe unravels. It's the ultimate backup drive with one glaring problem: we have no clue how to open the door, let alone step through. Perhaps the most haunting solution is ditching biology altogether. If vacuum decay erases atoms but leaves mathematical structures intact, encoding human consciousness into topological defects in spacetime or error-correcting codes within quantum fields might outlast the apocalypse. The concept, dubbed cosmic inheritance, treats consciousness as information patterns rather than physical processes. Think of it as saving a file in a format that doesn't care if the hard drive melts. Experiments in photonic quantum memory and topological qubits hint at ways to store data in physics-defying states, though scaling this to human minds remains the stuff of horizon science. Each of these strategies shares a common thread. They treat the universe not as an unshakable stage, but as a fragile construct that might need debugging. Whether through shields, escapes, or digital reincarnation, the message is clear. If reality's foundations are probabilistic, our survival may depend on learning to hack the code. The idea that reality itself might be a probabilistic house of cards forces us to confront a paradox at the heart of existence. Does fragility amplify our significance or render it meaningless? Existentialist thinkers like Jean-Paul Sartre argued that life's lack of inherent purpose isn't a flaw, it's an invitation. If the universe could unravel at any moment from a quantum hiccup, then every choice, every act of creation or connection becomes a defiant strike against the void. There's a raw beauty in building sandcastles knowing the tide is eternal. The more temporary the canvas, the bolder the brushstrokes. Buddhist philosophy arrives at a startlingly similar conclusion from a different angle. The concept of anicca, impermanence as the fundamental nature of reality, has been central to Eastern thought for millennia. Quantum tunneling's threat of vacuum decay mirrors ancient teachings that all phenomena are transient, from galaxies to thoughts. But rather than despair, this insight sparks liberation. The Tibetan sand mandala, painstakingly crafted only to be ritually destroyed, embodies this. Meaning isn't found in permanence but in the act of making. If even space-time is fleeting, then our struggles and joys aren't diminished, they're distilled to their essence. Yet there's tension here. Albert Camus' myth of Sisyphus pits humans against an indifferent universe where the struggle itself becomes the meaning. But what if the universe isn't just indifferent but unstable? Does the possibility of a cosmic reset button make our endeavors absurd or electrifying? Modern physics inadvertently resurrects an old theological debate. Is a universe with an expiration date designed to humble us or to spur urgency? The answers might lie not in theory but in action. After all, the same quantum laws that permit vacuum decay also enable photosynthesis, DNA mutations, and the firing of neurons that let us ponder these very questions. Perhaps the deepest irony is this: our awareness of existential fragility is itself a product of the same quantum randomness that threatens it. We're transient patterns in the cosmic foam, gazing back at the void and daring to assign value. That act, whether framed as existential rebellion, spiritual practice, or scientific inquiry, might be the most improbable tunneling event of all, consciousness leaping the barrier from chaos to meaning. Hollywood loves a good apocalypse, but when the end comes from quantum weirdness, the rules get gloriously twisted. Take Ant-Man diving into the quantum realm, where reality flickers like a broken hologram. The film turns tunneling into a visual spectacle, particles phasing through barriers, time distorting, even entire universes compacted into a suitcase. It's nonsense physics, sure, but it captures the existential thrill of quantum fragility. One wrong move and Scott Lang might not just shrink, he could unravel space-time itself. The movie's climax, where a time vortex threatens to erase existence, isn't far from theoretical false vacuum decay. Just swap the CGI for a bubble of true vacuum, and you've got a blockbuster version of Armageddon by quantum fluctuation. Then there's Portal's iconic gun, bending the laws of physics with every shot. The game's genius lies in making quantum tunneling tactile. Those shimmering orange and blue portals are basically cosmic cheat codes, letting players step through barriers like particles phasing through walls. But the subtext is darker. Gladios's infamous line, "The device is now more valuable than the organs and combined incomes of everyone in subject hometown here," It hints at the hubris of tampering with forces we barely understand. It's a dark joke with a cosmic punchline. Play God with quantum rules, and you might just delete the game board. 6 in Lose, the three-body problem takes it further, weaponizing quantum uncertainty in ways that haunt long after the last page. The Sophon's proton-sized supercomputers folded into higher dimensions exploit tunneling to interfere with Earth's particle accelerators, sabotaging scientific progress at its root. It's a chilling metaphor. When reality's deepest layers can be hacked, even knowledge itself becomes unreliable. The novel's climactic, dark forest theory suggests civilizations stay silent not out of shyness but fear, that any broadcast might attract beings who will preemptively trigger vacuum decay to eliminate rivals. Forget alien invasions. The ultimate threat is a neighbor hitting the cosmic reset button. Even indie media plays with these ideas. The cult game Control pits players against the Hiss, a resonant force that warps reality by exploiting quantum superposition. Offices twist into M.C. Escher nightmares, and co-workers recite eerie mantras, "You are a worm through time," as if space-time itself is glitching. It's artistic license, but the vibe is uncomfortably close to what a localized vacuum decay might feel like, reality stuttering like a corrupted video file. What makes these stories resonate isn't their accuracy, it's their honesty. They tap into a primal unease that beneath the orderly surface of atoms and orbits, the universe is fundamentally improvised. Whether it's Ant-Man's shrinking suit or the Sophon's quantum sabotage, pop culture reminds us that the cosmos isn't just stranger than we imagine. It's stranger than we can imagine, and sometimes that's a terror best explored with popcorn in hand. So here we stand, on the knife's edge of cosmic uncertainty, staring into the quantum abyss where particles cheat, space-time flickers, and entire universes might blink in and out of existence. The scenarios we've explored are equal parts terrifying and awe-inspiring. Vacuum decay erasing physics as we know it, black holes tunneling into white holes, dark matter whispering the universe toward phase transitions. But here's the twist. The very fragility of reality is what makes it so astonishing. The fact that existence could hinge on a single quantum dice roll doesn't diminish its grandeur, it amplifies it. We're part of a cosmic story where the rules aren't just written in stone, they're etched in probability, humming with potential. Yes, the risks are theoretical. The odds of vacuum decay unfolding in our cosmic neighborhood are vanishingly small. But that's not the point. What matters is how these ideas stretch our imaginations, forcing us to confront the universe not as a static stage but as a dynamic, evolving puzzle. Every experiment, every observation is a conversation with the unknown, a chance to decode the hidden language of quantum foam and false vacuums. And if there's one thing history teaches us, it's that the universe's deepest mysteries often start as footnotes in equations before rewriting reality itself. Carl Sagan once said we're made of star stuff, and he was right, but he might have added that we're also woven from quantum uncertainty, from the same flickering probabilities that power stars and threaten vacuums. That duality is the heart of the human experience. To gaze at the night sky with wonder while acknowledging it might one day rewrite itself without warning. So here's a question to leave you with, not just as viewers but as fellow explorers of this improbable cosmos. If the math ever predicted an inevitable cosmic doomsday, would you want to know? To brace for the end, or to live in blissful ignorance until the final quantum whisper? The answer says as much about us as it does about the universe. After all, curiosity is our compass even when it points toward the abyss.